Producing the top and bottom lids for steel barrels involves several precise steps. First, flat steel sheets are selected for their quality and thickness. These sheets are then fed into stamping machines equipped with custom molds that shape the lids under high pressure. The stamping process ensures the lids have consistent dimensions and strength. After stamping, the lids often undergo trimming to remove any excess material and achieve smooth edges. Some lids may also receive additional features, such as vent holes or reinforcing ribs, depending on the barrel's intended use. Bending the drum body involves shaping flat steel sheets into a cylindrical form. This is achieved using a rolling machine, which gradually curves the steel until the edges meet. Precision is essential to ensure a uniform shape and proper alignment for welding. The automatic welding process for joining the two sides of the barrel involves advanced machinery that ensures precision and consistency. Once the steel sheet is rolled into a cylindrical shape, it is placed into an automated welding machine. This machine uses techniques like arc welding or resistance welding to create a strong, continuous seam along the joint. Sensors and control systems monitor the weld quality in real time, adjusting parameters to maintain optimal conditions. Then, grooving machines emboss specific patterns onto the body of the barrel. These grooves serve multiple purposes. They enhance the structural strength, facilitate easier handling and stacking, and improve the barrel's overall durability. Fixing and welding the top and bottom lids to the barrel body is a critical step in ensuring the barrel is sealed and secure. After the lids are produced and inspected, they are positioned and aligned with the open ends of the barrel body. Automated welding machines then carefully weld the lids to the barrel, using techniques like arc welding or resistance welding. These machines ensure precise and strong welds that seal the barrel tightly, preventing leaks and maintaining the integrity of the contents inside. The automatic painting process in steel barrel production is a sophisticated step that enhances both the aesthetic appearance and functional durability of the barrels. Once the barrels are assembled and cleaned, they enter an automated painting line designed for industrial applications. First, the barrels are prepped by passing through a series of cleaning stations to remove any residual oils, dust, or contaminants that could affect paint adhesion. After cleaning, the barrels move into a primer application area where a uniform layer of primer is sprayed onto the surface. This primer helps improve paint adhesion and provides initial corrosion resistance. Next, the barrels enter the main painting chamber, where industrial-grade paint is applied. Automated spraying systems ensure even coverage of paint across all surfaces of the barrel, including the lids and grooves. The paint used is formulated to withstand harsh environments and provide long-lasting protection against corrosion. The hot spinning machine utilizes high heat and rotational force to shape metal workpieces on a lathe. By pressing tools against the heated, spinning metal, it achieves precise control over the thickness and dimensions of gas cylinders. The bottom closing operation is a crucial step in gas cylinder manufacturing, ensuring the cylinder's integrity and safety. After the cylinder body has been shaped through hot spinning, the open bottom end must be securely closed to create a sealed, pressure-resistant vessel. Heating. The bottom end of the cylindrical workpiece is heated to a high temperature, making the metal pliable and easier to manipulate. Mechanical pressing. Once sufficiently heated, the bottom end is mechanically pressed or spun closed. This operation involves using specialized tools and dies to fold and compress the metal into a tightly sealed bottom. Welding if needed. In some cases, an additional welding step is performed to ensure an airtight and secure closure. The welding adds extra strength and prevents any potential leaks. Inspection. After closing, the bottom of the cylinder is inspected for defects or weak spots to ensure it meets safety standards and can withstand high pressure. The bottom closing operation results in a robust, sealed end that can safely contain compressed gases, maintaining the cylinder's structural integrity and safety during use. The neck forming operation is an essential step in the gas cylinder manufacturing process, responsible for creating the top section where the valve assembly will be attached. This operation ensures that the neck is precisely formed to secure a leak-proof connection for the valve, which is critical for safe gas storage and usage. Heating. The top end of the cylinder is heated to make the metal pliable. This heating step is crucial as it ensures that the metal can be shaped without cracking or losing its structural integrity. Forming tool. Using a specially designed forming tool, the heated metal is gradually shaped into the neck. The tool applies controlled pressure to the metal, ensuring uniformity and precision in the neck's dimensions. Precision shaping. The shaping process is controlled to achieve the exact dimensions required for the valve fitting. This precision is vital for ensuring a secure and leak-proof connection. After forming, the neck is cooled and then thoroughly inspected for any defects or deviations from the specified dimensions. This inspection ensures that the neck meets all safety and quality standards. The second external and internal polishing process in gas cylinder manufacturing plays a critical role in enhancing surface finish, cleanliness, and safety of the cylinder. This step follows initial shaping and welding operations, aiming to refine both the exterior and interior surfaces. Specialized machines and abrasives are used to smooth and polish the outer surface of the cylinder. This removes any imperfections, weld marks, or rough edges left from previous manufacturing steps. The goal is to achieve a smooth, uniform surface that improves aesthetics and facilitates the application of protective coatings. Similarly, the interior of the cylinder undergoes polishing to remove weld spatter, burrs, and any roughness that could compromise the cylinder's integrity or contaminate stored gases. This process is crucial for ensuring cleanliness and preventing corrosion or gas contamination. The automatic paint spraying process in gas cylinder manufacturing is a crucial step that ensures both aesthetic appeal and long-term durability of the cylinders. Cylinders are first cleaned and prepared to ensure the surface is free from contaminants that could affect paint adhesion. Certain areas, such as valve openings or labeling zones, may be masked off to prevent paint from interfering with critical components. Automated paint spraying equipment applies a controlled layer of paint onto the cylinder surface. This equipment ensures even coverage and precise application of the paint. After painting, cylinders are conveyed through drying tunnels or ovens, where the paint is cured at controlled temperatures. Empty reservoir storage. Empty gas bottles are stored securely, awaiting the next phase of the maintenance process. Unscrewing. The caps of the bottles are unscrewed to access the interior for inspection. Selection sorting. Bottles are sorted based on their size, type, and material for appropriate refurbishment procedures. Manual sorting. This step involves a manual inspection to identify any visible defects or damage. Bottles undergo a stringent 10-year test to assess their structural integrity and safety for continued use. Emptying. Any remaining gas is emptied from the bottles in a controlled manner. Pre-screwing. After inspection and testing, the bottles are prepared for the next phase of refurbishment. The outer surface of the bottles undergoes shot blasting to remove old paint and rust. Zinc painting. A layer of zinc paint is applied to protect the bottles from corrosion. Drying. Bottles are dried thoroughly to ensure no moisture remains inside. Commercial pad printing. Important information such as safety instructions, manufacturer details, and capacity are pad printed onto the bottles. Decennial inspection. Periodic inspections every 10 years ensure ongoing safety and compliance with regulatory standards. Gas refilling. Bottles are refilled with the appropriate gas according to their specifications and intended use. Screwing on cap. Finally, caps are securely screwed back onto the bottles to seal them and prepare them for distribution or storage. The plate-to-cup draw process involves forming a flat metal plate into a cup-shaped object. This is achieved through deep drawing, where the plate is pressed into a die cavity by a punch, creating a seamless, hollow shape. Shell wash cleans gas bottle exteriors, removing dirt, grease, and contaminants, ensuring a clean surface for inspection and further processing. Inspection involves thorough examination of components for defects, conformity to specifications, and safety standards, ensuring reliability and suitability for their intended applications. Liner spinning is a metalworking process used to create cylindrical or conical shapes from sheet metal blanks. It involves clamping a metal disc onto a rotating mandrel while applying axial and radial pressure. As the mandrel spins, specialized tools gradually shape the metal into the desired form, achieving precise dimensions and uniform wall thickness. This method is favored for producing seamless, high-strength components such as pressure vessels, gas cylinders, and pipes. Heat treatment is a controlled process used to modify the properties of metals and alloys. It involves heating the material to specific temperatures, holding it at those temperatures for a precise duration, and then cooling it in a controlled manner. Machine porting refers to the process of modifying the intake and exhaust ports of an engine cylinder head to improve airflow. This is done using specialized tools to reshape and smooth the ports, optimizing the passage of air and fuel mixture in and out of the combustion chamber. Proper porting can enhance engine efficiency, power output, and overall performance, making it a crucial technique in high-performance engine tuning and racing applications. Liner inspection verifies structural integrity and detects defects in metal cylinder components. Carbon fiber wrapping involves applying carbon fiber fabric impregnated with resin onto surfaces to enhance strength, stiffness, and lightweight properties. Label application involves affixing identification or instructional labels onto products or components. Curing involves hardening materials through heat, chemical reaction, or ultraviolet light exposure. Sanding involves smoothing surfaces by abrasively removing imperfections and roughness from materials. Hydrotesting tests pressure vessels by filling them with water or another liquid to verify structural integrity under pressure. UV gel coating involves applying a liquid polymer resin onto surfaces and curing it using ultraviolet light to create a durable finish. Final inspection ensures products meet quality standards before distribution or use. Soraluce FLP 14000 as the Director of Operations, Matt Spagna highlights the machine's transformative impact on their production of seamless pressure vessels used in diverse industries such as electronics manufacturing, oil and gas exploration, and alternative fuels. Prior to the Soraluce FLP 14000, FIBA aimed to produce 240 vessels monthly, a target now achievable with the machine's capabilities. It operates 6 sets per 8-hour shift, representing a 50% productivity increase. The machine's automation allows it to handle multiple tubes in one setup, performing all 12 required machining steps without manual intervention. This includes saw cutting, roughing probing tools for both outer and inner diameters, probing for dimensional accuracy, and threading operations. Key technical advantages include the machine's extensive travel capacities, 14,000 millimeters longitudinal, 2,200 millimeters vertical, and 1,500 millimeters cross, and a universal head capable of drilling holes at a precise 45 angle. This capability was previously time-consuming, but is now efficiently managed by the Soraluce FLP 14,000. Operational efficiency is enhanced by integrated software that simplifies program selection and execution. The machine's ability to automatically measure and ensure correct positioning further reduces operator workload and improves accuracy. FIBA has praised the local support provided by Morris and Select Machining Technologies, which facilitated smooth installation and continues to offer rapid after-sales service, minimizing downtime and ensuring continuous production. The manufacturing process begins with cutting pipes to the required lengths. After cutting, the bottom part of the cylinder is formed. This involves shaping one end of the pipe to create a closed bottom. The process typically employs techniques such as deep drawing or spinning, ensuring that the bottom is securely sealed and can withstand high pressures. The neck of the cylinder is formed at the opposite end of the pipe. Heat treatment enhances the mechanical properties of the cylinder by heating it to a specific temperature and then cooling it under controlled conditions. This process involves phases such as austenitizing, quenching, and tempering. Austenitizing transforms the steel's microstructure. Quenching rapidly cools it to lock in these changes, and tempering alleviates any brittleness, improving the steel's strength, durability, and resistance to stress. This ensures the cylinder can withstand high pressures and harsh operating conditions. Neck cutting. Holes are drilled into the neck to allow for the installation of valves or other components. Threads are cut into the neck to facilitate the attachment of valves and regulators. This threading must be accurate and conform to industry standards to ensure compatibility with standard fittings. The water capacity of the cylinder is measured to determine its volume. This measurement ensures that the cylinder can hold the intended amount of gas or liquid and complies with regulatory requirements. A hydrostatic test is performed to check the cylinder's integrity and strength under pressure. The cylinder is filled with water and subjected to high pressure to detect any leaks or weaknesses in the structure. In addition to the hydro test, a separate leak test is conducted to ensure that the cylinder does not have any leaks that could compromise safety. Steam heating is applied to the cylinder to remove any moisture and ensure the interior is dry. This step is crucial for preventing corrosion and ensuring the longevity of the cylinder. The ISB internal shot blasting process cleans the interior surface of the cylinder. This step removes any residual contaminants or scale, ensuring a clean surface that is ready for the intended contents. The final step in the manufacturing process involves stamping essential data onto the cylinder. This information includes the manufacturer's details, serial number, manufacturing date, and specifications. Data stamping ensures traceability and compliance with industry regulations. Cutting and shaping steel plates is a precise process where boilermakers use oxyacetylene torches to cut the steel according to specific measurements and markings. This method ensures clean, accurate cuts. The cut plates are then passed through rollers, which bend and shape the steel to the required curvature, forming the boiler's main body and other essential components. These skilled professionals join the parts to form both the main body or shell of the boiler and its ancillary components, which include chimneys and pipes. The chimneys are vital for expelling toxic fumes safely, while the pipes manage the flow of water and fire, essential for the boiler's operation. Once all parts are welded together, the entire boiler assembly undergoes pressure testing. This test verifies the boiler's ability to withstand the operational pressures it will encounter, ensuring there are no leaks or weaknesses in the construction. Following successful pressure testing, the boiler is insulated with fiber blankets. These blankets are crucial for heat retention, enhancing the boiler's efficiency by minimizing heat loss. Repkin LPG cylinder welding machines are specialized devices designed to weld single circular seams on gas cylinder bodies using submerged arc welding SAW technology. These machines are engineered to meet high standards of welding quality and operational efficiency, catering specifically to the dimensions and requirements of LPG cylinders. Key features and technical specifications. The Repkin LPG cylinder welding machine offers several notable features and technical specifications. Welding capability. It can weld cylinders with diameters ranging from 200 millimeters to 750 millimeters and lengths from 200 millimeters to 500 millimeters. This flexibility allows it to handle a variety of cylinder sizes commonly used in the LPG industry. Continuous operation. The machine is designed for continuous operation, capable of running 24 hours a day, ensuring high productivity in industrial settings. Submerged arc welding. Utilizing SAW technology ensures deep weld penetration, uniform weld appearance, and minimal spattering, which are critical for welding gas cylinders reliably. Motor power and rotation. It is equipped with a 0.75 kilowatts motor and supports cylinder rotation speeds ranging from 0.2 to 2 revolutions per minute, RPM, providing optimal welding conditions. Control and automation. Controlled by a Japan Omron PLC and touchscreen interface, operators can easily set welding parameters, store different welding specifications, and retrieve them as needed. The system also includes fault alarms to alert operators to issues like stuck or blocked wire during welding. Flexibility and ease of use. The welding torch can be adjusted in multiple directions, up, down, side to side, and angled, which, combined with the rotary chuck and rolling wheel bracket support, allows for easy loading and unloading of cylinders. The machine's universal ball system ensures flexibility in positioning cylinders of varying lengths. Safety and monitoring. The machine features a robust sliding door with an inspection window made of steel plate, providing both strength and visibility into the welding process. This enhances safety while allowing operators to monitor welding progress. Additional equipment. It comes equipped with a Japan OTC XD600 SAW power source and includes a flux recovery and transport system capable of handling up to 100 kilograms of flux over distances up to 10 meters. The GRP, glass reinforced plastic, and FRP, fiberglass reinforced plastic, vertical vessel tank, filament winding machine represents a significant advancement in industrial manufacturing in Peru. This sophisticated machinery is designed to produce high-quality, durable vertical vessel tanks that are widely used in various industries, including chemical processing, water treatment, and oil and gas storage. The filament winding process involves winding resin-impregnated continuous filaments around a rotating mandrel in precise patterns. This method ensures optimal strength and durability, making the tanks highly resistant to corrosion, chemicals, and environmental stressors. The GRP-FRP tanks manufactured using this technology are lightweight yet strong, providing an excellent alternative to traditional metal tanks. In Peru, the adoption of this technology marks a pivotal shift towards modernized manufacturing processes. The country's industrial sector benefits significantly from the enhanced efficiency and reduced production costs associated with filament winding. The machinery's precision and automation reduce the likelihood of human error, ensuring consistent quality across all produced tanks. One notable application in Peru is the use of these tanks in water treatment facilities. Given the increasing demand for clean water and effective waste management solutions, the GRP-FRP tanks provide a reliable and long-lasting option for storing and treating water. Additionally, their resistance to harsh chemicals makes them ideal for chemical processing plants, where traditional metal tanks would quickly corrode. The implementation of the GRP-FRP vertical vessel tank filament winding machine also aligns with Peru's environmental sustainability goals. The production process generates minimal waste, and the resulting tanks have a longer lifespan, reducing the need for frequent replacements and thereby decreasing overall environmental impact. This process begins in the casting department, or foundry, where a mixture of metals is melted and cast into molds to form the basic shapes of the taps. After casting, these components undergo machining to refine their shapes and remove any rough edges. Once the initial machining is complete, the components are polished. Polishing is a critical step that provides a smooth and shiny surface finish, preparing the taps for the next stage of the process, electroplating. Polished components are transferred to the electroplating department, where they undergo a series of electrochemical treatments to coat them with nickel and chrome. This coating not only protects the brass components from corrosion, but also gives them an attractive chrome appearance. The electroplating process starts with loading the components onto jigs or hangers, which are then coated in rubber. A crane moves these loaded jigs to the electroplating section, where the components are dipped into a sequence of baths. The process is controlled by the electroplating specialist, who ensures the correct chemicals and metals are used and that the baths are maintained at the appropriate temperature. Initially, the components are cleaned in various tanks, with the first tank using ultrasound to remove polish residues from the smallest crevices. Another tank employs electronic cleaning to remove any oxides and scale, which is crucial for the nickel and chrome to properly adhere to the brass. The cleaned components are then dipped into a bath containing a nickel solution. This step involves multiple dips, with each dip adding a new layer of nickel to create a strong foundation for the subsequent layers. After the nickel plating, the components are washed and then immersed in an acid bath, which activates the surface for chrome plating. The final step in the electroplating process is the chrome bath, which gives the components their shiny silver finish. Electroplating is a highly regulated trade requiring trained professionals with a solid understanding of the chemical reactions involved and good proficiency in mathematics and science. The entire electroplating process takes about 90 minutes and is closely monitored by a plant controller.
Georgia Hydraulics International is a leading manufacturer of high-quality hydraulic and pneumatic cylinders, offering both standard NFPA-compliant models and custom-engineered solutions for diverse industries, including manufacturing, construction, military, mining, agriculture, forestry, and clean energy. The manufacturing process begins with design and engineering, where experienced engineers use advanced CAD and 3D imaging software to create precise models of cylinder components. This technology allows for rapid prototyping and seamless transition from design to production. Once the designs are finalized, the production phase utilizes state-of-the-art CNC automated machines to ensure precise fabrication of parts. These machines deliver exceptional accuracy, enabling the company to meet tight tolerances required for performance and durability. Quality control is integrated at every stage of manufacturing, Each component undergoes rigorous inspection and testing to ensure compliance with ISO 9001-2008 and ISO 14001-2004 standards. This commitment to quality guarantees reliable and long-lasting products that exceed customer expectations. During assembly, trained machinists carefully fit and test components, ensuring proper alignment and performance. Specialized cylinders, such as tandem cylinders and corrosion-resistant models, are assembled for applications requiring enhanced durability and efficiency. The final stage involves performance testing, where each cylinder is subjected to strict evaluations to confirm operational reliability under varying conditions. LD Machinery, located in Ningbo SE Port City, spans 10,000 square meters and employs over 100 skilled workers. With a history of over 20 years, specialize in manufacturing custom metal castings and hydraulic cylinders. As a privately owned Chinese company, we distribute our products across the Americas, Canada, Europe, Asia, and Australia. Since our founding in 1990, LD Machinery has implemented 3 primary production plants to meet customer needs: casting process, utilize advanced casting methods to create complex shapes more economically than alternative manufacturing techniques. The process involves melting materials at 1,600 degrees Celsius, pouring the liquid into molds, and allowing it to solidify into the desired shapes. This ensures precision and high-quality components. Advanced manufacturing. Our facility is equipped with state-of-the-art machinery, including CNC lathes, CNC centers, cutting machines, tapping machines, automatic welding machines, and cleaning systems. Additionally, employ professional engineers who design 3D models tailored to customer specifications. Our sales team ensures seamless communication with international clients. Produce a wide range of customized components such as hydraulic cylinders, cylinder parts, steel OEM parts, and aluminum covers. All manufacturing processes adhere to ISO 9001 quality standards, guaranteeing reliability and durability.